So here's an extended problem for a continuous probability question. Now, when it comes to probability questions in general for Saxon exams, you'll notice that a lot of the different probability types are mixed. So I'm just going to preface this question with the fact that this is a question where there's multiple probability types combined together. It obviously starts off with a continuous probability model that you can probably see before we even read the question, but just keep that in mind. When we do things in the textbook, everything is grouped together into their own categories. So you've got continuous probability in one chapter, chapter 15, you've got discrete probability in chapter 13, you've got binomial distribution in chapter 14, and so on and so forth. So when you do the problems from those exercises, for the most part, the questions that you're doing from them are questions for that specific topic. So what we need to do is try questions that combine topics together, because that's how we're going to be tested on SACs, and that's how we're going to be tested on exams as well. So it's really imperative that we source out these questions, whether they be from myself, from me making these questions, or from the review sections of the textbook, or from old exams, or from past SACs, or wherever you want to get them from. Just make sure that you're doing them. That's the most important thing. Now, just as a reminder, as I go through with all the videos, these questions I make from scratch, and if you need any, feel free to send me a message on Slack, and I'm more than happy to help you out with whatever questions you're looking for. I have plenty of questions that I've made over the past 6 years of tutoring. So yeah, let me know if you need anything. The amount of money won after playing a slot machine is defined by X dollars. X is purely the money made from the slot machine and doesn't consider the cost of playing. X is represented by a probability density function, P of X defined below. So this is the probability density function here. It's got a non-zero function here from X is greater or equal to 0, and it's defined as 0 otherwise. And the first question, determine A, always the same process. You find the integral of your function for its respective domain, and you make it equal 1, and you try and find the variable A. So let's go ahead and do that now. A multiplied by X multiplied by e to the power of negative X, and we're going to define this integral from 0 to infinity. And we're going to make it equal 1. So let's go ahead and solve for A. And we get A is equal to 1. Pretty straightforward. Let's just write the working out just to make this proper, set a good example. Ax e to the power of negative x dx is equal to 1, therefore A is equal to 1. Next question, determine the probability that x is less than 2. So we're going to take this same probability calculation. We're obviously just going to replace A with 1, which makes no difference to our calculation, and we're going to integrate from 0 to 2. So 2 will be our upper bound, 0 is going to be our lower bound, and we get that as our probability. The probability of that is equal to 1 minus 3e to the power of negative 2, and you can represent that as 3 over e squared if you want to, and we'll probably do that. Determine E of X. Let's determine E of X now. We take the same calculation from 0 to infinity. Actually, we'll just copy this top one. So we take the same calculation and we just multiply our whole function by X. So X multiplied by our original function, which is there, from 0 to infinity. This will be our expected value, and our expected value is $2. And I guess in this case, we are talking about dollars. So, this is the expected value. So I should just include the unit. In this context, we expect to make $2 playing the slot machines. It's the average return in the long run. That's how we kind of interpret this number. And it costs $2.50 to play the slot machine game. This kind of validates my answer from before, because the expected value is $2. It costs you $2.50 to play the slot machine game. And if you know anything about casinos, they're trying to make money. So they want to make the expected value of the game higher than the cost, because they'll be losing money, because they'll be paying more to customers. But yeah, that's just a small observation I just made. This is my first time going through this question, by the way. I made this a while ago, but I don't really know the answers in advance. I'm kind of going through it live and trying to break it down as I go through it. So determine the expected winnings or loss after playing the slot machine. After paying for the slot machine and playing the slot machine game. So the observation that I mentioned before kind of relates to this. If we're talking about the expected winnings, then we're talking about how much we earn, how much we expect to earn, minus how much we expect to pay. So that's how I would kind of describe this. So I'd just say expected winnings is equal to payout minus payout minus cost. So the expected payout is $2. We can't really say what the definitive payout is, but because we're talking about expected winnings, we'll just describe this as expected payout. So that would be $2. Now the cost is not expected or anything, it's just a flat cost of $2.50. So the expected winnings will just take into account the fact that we do pay $2.50 per game. So this would be negative 50 cents. Now, if it's negative 50 cents for expected winnings, that is the same as a 0.50 loss per game. Oh, I won't say that. I'll just say expected loss of 50 cents. What is the probability that you profit after playing the slot machine game? So in order for us to profit, a profit would mean that we get a payout of more than $2.50 because it costs us $2.50 to play the game. So the probability of making a profit would just be whatever probability is of making more than $2.50 from the slot machine. So what we do is we take the same calculation as above and we just calculate it from 2.5 or $2.50 all the way up to infinity, and we determine what the probability is. And that probability is there. Probability that you profit after playing the slot machine game. So we say probability X is greater than 2.5, and we get that ridiculous number there, 7 over 2 e to the power of negative 5 over 2. I know this doesn't say this in the question, but I feel like this question should be asking for it to a certain amount of decimal places to make it a bit easier to represent. So I'm going to change this question live and pretend it says, give my answer to 4 decimal places. If you play the slot machine 5 times, what is the probability that you make profit at least 3 out of the 5 times? Now, this is an interesting question because this is what I mentioned at the start of this video about different probability types combining. If we play the slot machine 5 times, what is the probability that we make you make profit at least 3 out of the 5 times? Now, the wording of that last part of the sentence is hinting towards binomial distribution. And the reason why we do use binomial distribution in this case is because we're kind of taking the event of making a profit and we're repeating that over multiple experiments or over multiple trials. So the probability of making a profit is constant for X amount of trials. It doesn't say that it doesn't change over time. They're not dependent events. You just assume that when you play a game, you have the same probability density function as so. So when we have a probability of making profit of 0.2873, we can safely assume that that is the case for all trials. So what I would say in this case is that P is equal to 0.2873. And we have 5 trials. And if we want to make profit at least 3 out of 5 times, then X is greater than or equal to 3. So we treat this as just a binomial distribution problem. And I can redefine this as Y is a binomial distribution with 5 trials and a probability of success of 0.2873. And therefore I can say, or I can solve this question by just evaluating Y being greater than or equal to 3. And I can just evaluate this on the calculator. But before I do so, I just want to make sure that this makes sense. We have a certain event, which was a continuous event, and there's a certain outcome that we wanted to focus on. So that outcome was making a profit or making more than $2.50 from the slot machine by itself. And then that continuous event, we turned it into a binomial or a repeated event because we repeated that same experiment multiple times. So we evaluated the initial probability through our continuous model or our continuous density function, and then that specific outcome we repeated through a binomial distribution. So it's essentially evaluating one probability from another probability being repeated. Or we're evaluating our new probability from an old experiment being repeated. Hopefully that makes sense. We're taking one continuous event, or we're taking one event which was calculated through a continuous function, and we're repeating that over multiple trials, which is a binomial distribution. I'm hoping that explanation makes sense. So we go to interactive, distribution, discrete, binomial CDF. If we make profit at least 3 out of the 5 times, then the lower bound will be equal to or greater than 3. The upper bound would be 5 because that's the number of trials, and the probability of success is 0.2873. Now just keep in mind, I know this is a shortened decimal, so what I'm actually going to do is I'm just going to copy out this decimal and put that decimal in there, just to make sure that we don't have any rounding error when doing our evaluation. So I'm not going to type them all in because it's going to be hard to remember, but I'm just going to copy and paste it in this calculation line here, which I can safely do. And then I end up getting to 4 decimal places, 0.1467 for this answer.